All right. So what we were working on last class were differential equations that were separable, meaning you could get the x and the y terms to be separated from one another. So, some variation of y dy on the left-hand side, some variation of x dx on the right-hand side, and then you would integrate both sides. This is a technique that you would use when you want to take a differential equation that is not separable, but make it separable. All right. So basically, we're manufacturing proportionality. The idea is that this is not, if I were to solve this for dy dx, which I can do that immediately, I'll subtract this guy from both sides. I'll just shoot it over there. We'd be looking at 3xy dy equals negative that. So I'll just write it as y squared minus x squared dx. Now, at this point, no matter how hard I try in this current form, there's no way to get just y's on one side and just x's on the other. All right? So I might even try something like, all right, well, let me just divide out the dx and divide out the 3xy. So dx from both sides, 3xy from both sides. So this would become dy dx equals y squared minus x squared over 3xy. All right. So you're like, oh, okay, I'll just take the antiderivative of that. Well, good luck, because it's not solely in terms of x. It's not solely in terms of y. There's no way to break apart the x from the y. But if I do a substitution, if I swap out the y for vx, I'm replacing y with something I know to be in proportion. All right, so v is a new function. So kind of like u substitution, where u is some new function. V is some new function, but it's an unknown function that allows x and y to be in proportion with one another. So dy dx would be equal to vx squared minus x squared over 3x times the vx. All right, so let's just play this out a little bit on the right-hand side. We would have v squared x squared minus x squared over 3vx squared. Now we have a common x squared in each term. So I could divide that out. And I would have, looks like v squared minus 1 over 3v. All right? That's kind of a problem because my left-hand side is dy dx. Now I have v's in there. Well, the dy dx has to go. Question? Where did I come up with the what? The v? This v? All right, and speaking of that, if we were to take a look at this guy over here, y equals vx, I can take the derivative of that in terms of x. Dy dx would be equal to, this would be a product rule, the first function times the derivative of the second, derivative of x is 1, plus the second function, x, times the derivative of the first, which would be dv dx. Okay, so a little implicit differentiation. All right, so we swapped out the y for a vx. Now we can actually swap out the dy dx for a v plus x dv dx. All right. So v plus x dv dx is going in for dy dx. If it's a homogeneous differential equation, yeah. Okay. So now I have a new differential equation based on this substitution, only containing v's and x's, which is what I wanted. For better or for worse, that needed to happen. So I'm going to solve it. I'm going to move some stuff around. I'll subtract a v from both sides. And I'll be looking at x times dv dx equals. The other one, I need a common denominator, so I'm going to make that v a v over 1. And then multiply top and bottom by 3b. So we'd be looking at v squared minus 1 minus 3v squared over 3b. All right. Now we have to do a little bit of housekeeping. There's some combining of like terms that can happen. I'm going to move this back up to the top for my next step. So x dv dx would be equal to negative 2v squared minus 1 over 3v. All right, all of that was to get a differential equation that was not something we could solve in its original form into a form that can be solved using techniques that we already know. All right, I can now separate my variables. I can get my v's on one side and my x's on the other side. So I'd be looking at 3v over negative 2v squared minus 1 dv equals 1 over x dx. All right, so I'm just multiplying by reciprocals. Multiply both sides by 1 over x. Multiply both sides by the reciprocal of the nasty fraction on the right. And then multiply both sides by dx. Now I can integrate. Right-hand side's easy. That's just ln of x plus c. Left-hand side actually isn't that bad either, because the denominator, if I take its derivative, I would get negative 4v. That's a multiple of 3v. All right, so this is also a natural log. ln of the bottom if I just left it like this, I would have a negative 4v. I don't want a negative 4, but I do want a 3. All right, so that's a little correction on the fly. That's to save you from having to do u substitution. You're welcome to do u substitution, but as you move forward, you want to get to a point where you're not always defining a u every time you go to take an integral. It's just going to slow you down. All right. So again, if I were to just check this by taking the derivative, I'd get 1 over negative 2v squared minus 1. The derivative of this would be negative 4v. I don't want the negative 4, so that's why this is here. Get rid of that. I do want a 3, because there's a 3 here, so that's why that's there. So it's a little correction on the fly. All right. Anyway, a little bit more housekeeping. What I'm going to do is multiply both sides by a negative 4/3, because my goal here is to get the v alone. So ln of negative 2v squared minus 1 would be equal to negative 4/3 ln of x plus c. All right, so I multiply both sides by the reciprocal of the coefficient on the left-hand side. I wanted this to go away, so I multiply both sides by negative 4/3. Goes away here, it becomes a coefficient of the natural log of x. When it gets multiplied, you multiply negative 4/3 by the c absorbs the negative 4/3. Alright, so that's why it's just a c. Rewrite log base e, negative 2v squared minus 1. Convert over into exponential form. So this would be e to the negative 4/3 ln x plus c. And that would be equal to negative 2v squared minus 1. Rewrite the left-hand side. And this is just a whole lot of pre-calc, really, because when you think about it, where did the calculus happen? Right from here to here. Just this step to this step. Everything else is some kind of algebra or pre-calc content knowledge, right? So, e to the negative 4/3 ln of x times e to the c. That we've talked about a few times, most recently last class, and that is if you have a sum within an exponent, you can break that up, keep the base, add the exponents just in reverse. Right? So this was exponential e to the power times e to the c before you kept the base and added the exponents to get this simplified. All right. E to the c is what? That's c. So we're looking at c e to the negative 4/3 ln of x. A rule for logs: the exponent, or the coefficient becomes the exponent. Exponent jumps over to log like a frog, as Miss Hamilton would say. So we have c e to the ln of x being raised to the negative 4/3 power. So x to the negative 4/3. All right. Now, it's kind of weird, but this is my license to drop the absolute value. That power relationship, I can now drop the absolute value around the x because it's being raised to an even power. The top number in a fractional exponent is the power it's being raised to. If a number is being raised to an even power, it's going to become a positive result. So I don't have to worry about the natural log being negative anymore, so I don't need the absolute value symbol. And so this cleans up because e of ln cancels. They're inverses of one another, so we're looking at cx to the negative 4/3. That doesn't look like a 3. So let me fix it. On the right-hand side, we have still the absolute negative, geez Louise. Let me just bring it up a little bit. It's going to be absolute negative 2v squared minus 1. All right. Now, our question was presented in terms of x's and y's. I have a solution to a differential equation, but it's in terms of x's and v's. So that v has to go. All right. So how can we swap out the v? Well, the rule that we're applying is that y is equal to vx. So therefore, v has to be the same as y over x. So I can replace my v with a y over x. Okay, so to clean it up further, actually do a good chunk of things here. I'll start with the obvious thing, actually square the x and the y. So negative 2y squared over x squared minus 1. Now, an absolute value is telling us that the result can be positive or negative. So I could write, instead of the absolute value, plus or minus negative 2y squared over x squared minus 1. And that would be equal to cx to the negative 4/3. But then I can actually just drop the plus or minus. Because if I were to divide both sides by plus or minus 1, the c would absorb that. And it would still become cx to the negative 4/3. All right, and since our goal here is to just solve for y in terms of x, really the only stuff that remains would be to multiply through with an x squared. So multiply everything by x squared. And we would get cx, you'd have to add negative 4/3 and 2, and it'll become 2/3. Because we have a denominator of x squared that I want to clear out. All right, and so that's going to be equal to negative 2y squared minus x squared. Add x squared to both sides. Negative 2y squared equals cx to the 2/3 minus x squared. Divide by the negative 2. Divide each part by the negative 2. We're looking at y squared equals cx to the 2/3 plus 1/2 x squared. And then the last step would be to take the root of both sides. In which case, y would be equal to the square root of cx to the 2/3 plus 1/2 x squared. Normally I would say plus or minus, but there's really no way in which this could be a negative. So the positive is all we need. It's not a problem if you put the plus or minus stuff. You can look at that. What page is this? I lost it. It's a 57, like a long time ago. I grew